Good afternoon, and welcome to today's technical deep dive of Extreme Performance Theory vSphere Compute and Memory Scheduler. My name is Xunjia Lu. I'm a developer working on ESX resource management team. What do? I mostly tune scheduling algorithms, design new policies, and fix bugs. So if you have any questions or comments or concerns or likes or dislikes about our resource management stack, please come talk to us, and we'd love to hear your feedback in order to make our product even better going forward. So every year we get rid of something old from the talk and add something new to the talk around the lines of new policies, new behavior, new hardware trend we're seeing from the field, as well as interesting customer cases that might have educational meaning for a broader audience. So hopefully by the end of this talk, you'll walk away with a much better understanding of resource management stack in general. Since we have a pretty tight schedule, if I may ask to postpone all the questions towards the end, we'll have a Q&A session towards the end, okay? All right, so let's get started. The usual disclaimer, please take a minute. I'd like to kickstart by posing a question. What is scheduling, and why do we need scheduling? Well, the reason why we need scheduling is pretty straightforward, right? Resource costs money, and we only have a limited amount of resource, so that we need to schedule efficiently. If we have an unlimited or indefinitely powerful system, we don't need scheduling. We just throw the workload on the system, it just runs, right? Scheduling problem is common across different fields, and interesting, a lot of people have defined this problem before, and it sort of aligns with software data center philosophy of how scheduling should work, right? It's about allocating resource. It's about assignment of different tasks. It's about priority of different tasks. And it's about expected output of those scheduling decisions. So with this in mind, here's today's schedule of our journey into talking about resource management. We'll start by talking about CPU scheduler. We'll talk about memory management. And we'll go down and talk about NUMA scheduler, which sort of touches both the CPU and the memory side. And we'll wrap up the discussion with VM sizing and host configuration considerations. All right, CPU scheduler. The goal of CPU scheduler is twofold. First is try to give high CPU utilization on your system, and at the same time provide high application throughput, make it run as good as possible, right? The second goal, which may or may not align with the first goal, is to ensure fairness across your workload on the system. The fairness is defined by shares, reservation, or limit, which sort of are the input into the scheduler. So this is a typical screen. You'll see how you configure CPU resource settings, right? You specify share, you specify reservation, you specify limit. This applies to your VM or resource pool in general. And the scheduler takes these inputs into considerations. As an output, we dispatch workloads onto different CPUs. So the scheduling question can be answered by when to run which workload and on what CPU. So let's talk about when. When would the scheduler run? Scheduler runs in three different cases. First case, it's what we call wake up, right? System is idle, new VM powered on, new vCPU got woken up, so scheduler decided to come in and run the workload. The second case is when the workload goes to sleep or halt, or saying, I'll wait for some event to happen. Say, hey, I'm waiting, run something else. The third case is when scheduler preempts the current running one to run some higher priority threads, right? So the current one is running happily on the system, and scheduler thinks that, oh, there's some higher priority will just become ready to run. I should probably run a high priority one instead of running you. And then scheduler decides to kick in and deschedule the current running world on top of from the local CPU. So we talk about priority. What is priority? Or which workload is more important than the others? Oh, by the way, world is a synchronyms of threads or processes we use in ESX. So what we run is worlds in ready queue, with the least consumed CPU time over the fair share. And this sort of defines the priority. What does this mean? This means that for two VMs, if they have the same fair share, we prefer to run the VM with a lower CPU consume time. On the other hand, if two VMs had the same CPU consumption, we prefer to run the VM with a higher fair share because it's more important. And this is how we define priority when we try to choose different workloads. Now, the last question is where to run this VM or this workload. And this is really a load balancing question. And the first foremost considerations we have is CPU load. We want to balance the CPU load across the system. We don't want everything to run on CPU 0 when there's 10 other CPUs staying idle, not doing anything. We also want to preserve cache state and minimize migration cost. Migration costs lose efficiency, right? But this is really a trade-off between utilization and migration cost, right? If you think about this, if the local CPU decides to wait, or the local running will decide to wait, you have two choices. You can either make the CPU stay idle, not run anything, or can pull a remote workload onto the local CPU to let it run. But by pulling a stuff from remote CPU to the local CPU, you're probably going to lose some cache state. But if you don't do such a thing, you lose utilization because you're making the local CPU idle. So scheduler is trying to strike a balance between these two decisions and try to make a smart decision for your application to be performant. The third consideration is about reducing contention. Contention can come from hardware, such as hyperthread contention, which we'll talk about in a minute, or last level cache contention. It can also come from the same VM when you have multiple vCPUs. For example, we want to spread the vCPUs across different physical cores as much as possible rather than keep every single vCPU from one single VM onto the same core. That's less efficient. The last point the scheduler tries to consider is the communication pattern between different workloads or different contexts. It could be VM talking to each other, or it could be VM talking to a networking thread. We think that frequent communication implies data sharing. And with data sharing, we want to put data closely together, maybe on a single last level cache or a single NUMA node. And the schedulers try to automatically detect this sort of pattern and make such a decision. So these are the considerations of scheduling policy. But in order to view what the scheduler actually, how the scheduler actually try to schedule stuff, we need some tools to help us visualize the stats, right? So ESS Top is such a great tool that we can use for performance monitoring. And this is a quick recap on ESS Top if you guys are not familiar with this. It's basically a top for ESX, which have different views of CPU, memory, disk, etc. And CPU is the one we're interested in right now. So for real-time monitoring, just type ESS Top into the shell or terminal, and you'll get this screen. And for batched mode, the batched mode is a useful tool to help you collect stats for offline study. You can specify how much snapshot I should collect, how many snapshots I should collect, and each snapshot is apart by like X amount of seconds. And perf mode is a great tool to analyze those offline statistics. A few new changes in 6.5 related to ESS Top is that first we add some new counters to actually help you understand the turbo mode of frequency scaling, which is called A-perf to M-perf ratio in the ESS Top power tab. The second is we changed some scheduling accounting implementations so that the ESS Top will be more intuitive. And we'll see this example in a minute. So here's the tool, and how does a VM look like? This is sort of what a VM looks like. We have two VMs, VM0 and VM1, and we expand into the view of the VM by specifying group ID, which sort of gives us this screen. The important part is that there's two vCPUs, vCPU 0 and vCPU 1. But also notice there's a whole bunch of other threads underneath this group. Should I be worried about them consuming too much CPU time? Well, not really, because these threads are just sitting there in case there's something needs to be done. But most of the time, their runtime is not very significant. So the key takeaway here is that a virtual machine consists of more than just the 2 vCPU world. It has all other threads as well. So 2 of the most important or mostly commonly used stats from CPU scheduler counting is usage or use time versus utilization or runtime. So what's the difference? Same snapshot, same group, same VM. What we see here is that these 2 vCPUs, if we look at the use time, it says 130% of the use time is logged. And the runtime is around 100%. Why is this the case? How come used is more than 100%? How can a vCPU use more than 100%? Why do we need these 2 numbers? Can we just have one number and be done with it? Well, actually, used and run are trying to capture really different things, and we cannot go with one without the other. So the runtime is actually based on clock time, meaning that during this 2-second snapshot of ES's top screen, if the vCPU runs for 2 seconds, the runtime will be 100%. If the vCPU runs for only 1 second, the runtime will be 50%, right? It's pretty straightforward. But use time, on the other hand, is trying to capture the amount of work that is being done during this 2-second period of time. So what's the difference? The amount of work depends on frequency scaling, depends on contention from hyperthread. So let's first talk about frequency scaling. So your processor has a nominal frequency, say 2 gigahertz, right? When a turbo mode comes in, this frequency becomes, say, 3 gigahertz, right? Because of this, the amount of work done in 2-second period of time will be different in the 3 gigahertz case versus 2 gigahertz case, right? In 3 gigahertz case, you do more work, and use time is trying to capture this. We also see an interesting case where a customer complained that the use time he sees is always 60% from the runtime. So it turns out that he has a knob in the BIOS that somehow limits the frequency to 60% of nominal frequency, and that's why he's seeing a use time being lower than the runtime, which sort of actually honestly reflects the amount of work done as well. But what about hyperthread contention? Hyperthread contention is something we easily ignore or doesn't pay too much attention to, and I'd like to talk about this for a second. So how can we have hyperthread contention? What does it mean? So in order to understand hyperthread contention, we first need to understand what hyperthread is and what's the benefit of using hyperthread. So here's a graph of showing hyperthread throughput gain. So the x-axis is a set of different benchmarks from Spec CPU 2006. The y-axis is the normalized throughput gain from hyperthreaded setup versus the baseline. So what's the setup? So the baseline case, for each workload, the goal is that we always run twice the same workload. In the baseline case, these workloads are placed on a single core, same hyperthread, and they run in sequence. So we finish the first iteration of the workload and we run the second iteration. For the HT setup, we take these 2 workloads and run them simultaneously on 2 hyperthreads of a core. As we can see here, using the hyperthreaded setup, we can have an efficiency gain from anywhere from 5% to 40%, which is a pretty good throughput improvement. But as we all know from life, nothing comes free. So why? What's the catch here? So the catch here is that with this hyperthreaded setup, each thread runs slower compared to the case when it has a dedicated thread, dedicated core. So same setup, x-axis is the benchmark, y-axis this time is the runtime of each workload iteration. As you can see here from the baseline case, the workload finishes much faster than the hyperthreaded case. The slowdown with the hyperthreaded case is actually anywhere from 1.5 to 1.9x slower. Notice we never go beyond 2x because that implies there's no throughput gain, only throughput loss, right? So what does this mean? How can I make sense of this? So hyperthread improves throughput, as we see before. But at the same time, each vCPU or each thread or each world might run slower with contention when your hyper-twin or the one next to is busy. So the easy way to think about this that I use is that think about a case where you have 2 cores or 1 core but 2 hyperthreads. Of course, the 2-core case will be more powerful, right? So that would be the difference. So ESX scheduler is really smart that it is hyper-threading aware. What this means is try to make smart load balancing decisions based on how hyperthreads of a single core are utilized, which means that the same amount of run percent might translate into different amount of used percent, depending on your hyperthread performance. So for example, if you're running and your partner hyperthread is also running, like 100% busy, so the 100% runtime you see on the local thread might only translate to 70% use time, indicating the fact that you have a 30% efficiency loss due to hyperthread contention. So what's the guideline here? I would suggest we always enable hyperthread by default just for the extra throughput, but also at the same time be aware of that hyperthread contention that might make each individual thread runs a little bit slower. I put a smiley face here because it might not be a bad thing because it's a sort of a benign contention, right? If you don't have hyperthread contention, you don't have throughput gain, you don't get anything from hyperthread. But as long as you understand what's going on underneath, we should be good. So we talk about use and run, but there's all other sort of matrix. So where are they coming from? So let's try to walk through a lifetime of a scheduling decision and see what's actually happening. For a VM, suppose at T0, it's waiting. It's just sitting there waiting for something to happen. And T1, it decides to run for some reasons. Maybe there's a networking packet coming, maybe the user types something in the keyboard, it decides to run. So the T1, actually, the block A is actually saying that the scheduling cost of the scheduler tries to decide this world should run. And once the scheduler finishes this decision, we transition to T2, which is the block B, representing the queuing time. Say at T3, we finally decided to pick up the world and execute the world. In those cases, the block C represents the actual execution of the thread from T3 to T8. Now, it's possible at T4, some interrupt happened, right? Some event happened that sort of temporarily paused execution of C to process interrupt. This time here is showed as D, which is interrupted time. There might be another case at T6 where, say, the hyper-twin of the current thread become busy or the frequency scaling decide to kick in. And then this period of time, T6 to C7, is the period of time where we have some efficiency loss. We want to capture that as well. So the wait time you see from stats is the gray box. The ready time consists of the queuing time, which is B, as well as the scheduling overhead, which is A. So should I be worried about scheduling overhead? Scheduling overhead is minimal. It's around microseconds level. So unless your workload sleeps and wakes up every couple of times per millisecond, you probably don't need to worry about this. Runtime, which is the utilization, as I mentioned before, is the green bar. Now the tricky part comes here. So the D, the interrupt time, is what we call overlap time, which needs to be taken out from the runtime to actually correctly reflect the execution or the amount of work done for this VM. And this D is actually doing work for this VM. We need to add this back again as system time. So adding all these together, what used actually is equals to run plus system time minus the overlap time and adjusted by the frequency loss. Now notice the E here. In case of turbo mode, right, you actually don't have an efficiency loss. You have efficiency gain because you're only at a higher frequency. In those cases, the E will actually be a negative value, indicating that there's a gain on top of the use time. So we talk about use and talk about run. So what about system time? So here's 2 screenshots from vSphere 6.0 and 6.5. Let's see if you can spot the difference here. 2 VMs running NetPerf. Let's, for argument's sake, think these 2 are using the same amount of CPU. And then the difference here is that in 6.0, the runtime is 130, but use time is 160. But in 6.5, the use and run is approximately the same. Why? Well, because in 6.5, we actually moved some of the system time into the runtime of the VM. As you can notice here, the system time in 6.0 is much higher than the system time here in 6.5. This is mostly to help you visualize accounting more intuitively. At the same time, which is not shown here, is that the overlap time become more and more negligible. So you probably don't need to worry about overlap time at all going forward. So another interesting part is that the group stats are different from a per world or per vCPU stats. So here's an interesting snapshot. VM ready time, 23%. How many of you think this is bad? Right. So ready time guideline is 5%, right? It's probably going to be tricky, and 10% is probably going to be bad. I have 23% here. It's pretty bad. But is it? So if we expand this view into this VM, what we see here is that we have a lot of vCPUs here. In this specific case, we actually have 128 vCPUs in this VM. And all these ready time adds up to 23%. But if we look at each individual vCPU, the ready time is very negligible. So what this means is that we need to be careful of looking at the ready time. So the ready time per group is the sum of everything. But what we really care about and what the guideline says about 5 to 10% ready time applies to per thread. So the group stats is an aggregation of all the per world stats, and we need to either look at normalized ready time or per thread ready time. So let's talk about ready time a bit more. How much impact would ready time have on my workload? Here's an example. We're running Java workload. We have ready time at x-axis, and the y-axis the throughput. With 18% of ready time, we see 15% of throughput drop. This is pretty realistic in this Java workload because it's mostly CPU bound. If you lose 18%, you run less, which is sort of proportionate to the time you lost. But if you look at latency benchmark, it's completely different, right? So Redis is an in-memory key value store, and this benchmark is trying to measure the operation latency for each read and write. So we have two lines, spiky and flat. So what's the difference here? The spiky line, which is the blue line, indicating a ready time induced by a very frequent but short running container, when the flat line indicating a container of longer running but less frequent container. In these cases, they can always trigger the same amount of ready time contention, but the impact on the y-axis, which is the tail latency, 99.99% latency, will be very different. In these cases, the spiky one has a less impact on latency, while the flat case has a higher impact on latency, which is almost 75% higher of the latency regression. So latency really depends on the competing workload's characteristics. If you really care about tail latency, try use latency sensitivity settings for our VMs. The last point I want to talk about is co-scheduling. Why do we need co-scheduling of a VM if we have multiple vCPUs? Well, we need co-scheduling because we don't want one single vCPU to take all the CPU resource of this VM. We want to bound the execution jitter or execution skew among all the vCPUs of a single VM. But we don't do such a thing by always running all the vCPUs all at the same time. What we do is scheduler is pretty smart of always running a subset of vCPUs at any given point of time so that we don't need to do this GAN scheduling. This is very efficient in a consolidated setup where you have more vCPUs than the physical threads or physical PCPUs or core on the system. But what if you see a high co-stop time? What should we be looking at? First thing to check if there's resource contention. What people don't realize is that ready time and co-stop time sort of go hand in hand sometimes. If you have resource contention, you might not run some vCPUs And if those vCPUs happen to be the slower one, you will cold stop the fast one. So in this case, you will have cold stop. The second thing to check is the VM wait, which is the non-idle wait of the VM, which represent the time of spending on waiting for IOs or memory page to be swapping, all those things. In those cases, vCPU needs to be paused so that after the event is done, we can resume execution. So these are all about CPU scheduler. Let's switch topic and talk about memory, which is a more interesting topic, because it's less flexible. The goal of memory management is that we want to allow memory overcommitment by allowing VM to have more provision or more configured memory than the host size. At the same time, we want to hide or handle the transient memory pressure so that the application don't see this. The way to think about this is that if you have a total memory size of, say, 4 GB, part of them is allocated, part of them is not allocated, right? So you have 4 GB of VM, 2 GB might be allocated, 2 GB might be free. But within those 2 GB of allocated memory, there is part of them that is actively used. But another part is idle, right? You allocated it, but you don't use it. So what memory reclamation try to do is try to take back those idle memories so that you can give that to somebody else. Reclamation happens when you have consumed memory that is greater than what you're entitled to have. Entitled to have is defined by sort of share, limit, and reservation as similar things we see for CPU scheduler. And the reclamation happens in different stages, right? We first try to page share, and then we try ballooning and try compression. At the end, we try host swapping. So this is a progressively more expensive operation from left to right. Right? Page sharing is least expensive when the host swapping is most expensive. And along this path, we start to break large pages. But what about large pages? Should I be using large pages? What we see is that if you use large pages across guest and hypervisor, you're actually going to see around 10% to 30% improvement on throughput. However, one concern on large page is that we don't really do page sharing within large pages, right? We cannot page share a large page. So the page sharing is also good because it avoids ballooning or compression or swapping. So what happened is vSphere 6.0, which is one release before, is that we noticed this thing and then we decide to add a new state of memory, clear state, which is when we start to proactively break large pages when we notice that there might be a transient memory pressure, so that by the time we actually have a memory pressure, stuff can be shared. So the bottom line is enable large pages, the memory scheduler will take care of the rest. So let's look at an example of transient memory pressure. Here we have a couple of VMs running a swing bench. We first power, so all the VMs are powered on but sitting idle. We first start workload on 2 VMs, VM1 and VM2. Everything is fine because 4 GB times 2 is 8 GB and host is 16 GB. But now we start to work on a third VM for a period of time and let it stop. So what happened was that we have a transient period where the host memory actually getting some pressure. But it's not really hard pressure because we still only have 3 VMs, each with 4 gig, but the host has 16 gig, so we're still okay. So what happened here is that there's no impact on VM's performance. However, if we see those counters in the bottom graph, we have balloon and swap and compress and share. There's some stuff happening, some operations happening. However, if you only look at balloon counters, for example, you might have the wrong conclusion that, oh, the memory scheduler is doing something. I must be having some memory pressure, which might mean that I have a performance degradation. But not true, because in those cases, VM1 and VM2 are happily running. There's no impact. So what we should be looking for? What does it look like when we actually have a pressure or performance degradation? Same setup, 2 VMs running, but T20 here, we start all the VMs. We start all 6 VMs. Each consumes 4 GB. 4 times 6, 24 GB, and the host only have 16 GB. There's no way this memory will fit into the physical RAM. So in those cases, we see performance degradation for VM1 and VM2 because we start swapping. So what should be looking out for is actually the swap-in rate. If we start to page in memory pages from the disk, the VM will take a performance hit. Rule of thumb, there's two types of memory overcommitment. The first type is configured memory overcommitment, where you actually sum up all the config size of the VM and compare it with the host memory size. The second case is active memory overcommit, which is the sum of the total actively used memory compared to the host memory size. Active overcommit, if it reaches 1, we have a higher likelihood or higher chance of performance degradation because you're right at the boundary of, mem scheduler tries to do page sharing, ballooning, compression, swapping, which might hurt performance. But on the other hand, config memory overcommitment, if you're not using all those config memory, is totally okay. Because we mostly reclaim memories from the idle pool. So the key guideline is that we always should aim for high consolidation while keeping down the active memory overcommitment. Make sense? All right, let's talk about NUMA scheduler. Just curious, how many of you have a NUMA system deployed on your data center? And how many of you, among those have the NUMA system deployed, how many of you have to think about NUMA scheduling? Great. Well, for us, we want to help you to make these decisions as good or as easy as possible going forward. Let's talk about NUMA scheduler. What is NUMA? NUMA is basically a non-uniform memory access model or system architecture where each node, that's a logical concept, each node has a set of CPU cores, a set of memory, and probably a set of devices as well. And the trick here is that access between a local node, among local node from CPU to memory, or from remote node, which is local CPU to remote memory, can be anywhere different from 30% slower or 200% slower. There was a confusion about NUMA node versus sockets. People tend to think these two are the same things, where actually they're not. In some machines, they might have multiple NUMA nodes per socket. In some other machines, which is less common, you might have multiple sockets per NUMA node. Two packages become the same NUMA domain. So the multiple NUMA per socket is something that Intel releases on Haswell chips, which is called cluster on die, and we'll talk about that in a minute. So the idea is that if you can fit smaller VMs on the same NUMA node, you can just throw the VM at the system, and NUMA scheduler will handle this automatically. And database is one example of a NUMA-sensitive workload. The goal or the job of NUMA scheduler are two things. NUMA scheduler need to do load balancing and try to balance VMs across different NUMA nodes, whether you have 2 NUMA nodes, 4 NUMA nodes, 8 NUMA nodes. It also tries to expose virtual NUMA-ness to the guest OS or guest application so that the whole stack can align properly for the best performance. Let's talk about load balancing first. Two considerations of load balancing. First, initial placement, right? We need to figure out where to place this VM when it's first powered on. But we have no data when the VM just powered on, whether how much CPU is going to use, how much memory it's going to use. But we can look at the current system state and decide, based on the current load of different nodes, where it's best, with higher probability that this guy will run the best. And we also have a periodic rebalancing algorithm where every 2 seconds, we look at the state of the system and figure out, should I move this VM here? Would it be better? Or should I swap these two VMs placement so that it would be better? The better is defined by better load balancer, better load balancing, better memory locality, and better communication sharing, and better fairness. So let's see how this is actually working in action. So here's an interesting plot. Let's take a minute here. What this is trying to say is we're running a TPC-V benchmark, which is multiple VM, multiple group benchmark. In this case, we have 4 groups. Each group have 3 VMs. Okay, so total 12 VMs. The x-axis is time, right? It's a time series plot. The y-axis here is pCPU number. PCPU 0 to PCPU 120. And this system happened to have 4 NUMA nodes. It happened to be the case that each horizontal bar is a NUMA node, and each dot on this graph is one placement decision of a VM for a given point of time. A couple of interesting points. First, if we look at group 2 and group 4, VMs tends to stay at a single NUMA node. What this means is that NUMA decisions are pretty sticky. Right? Once you make a decision, it's very expensive to change that decision because you need to move the memory, move the CPU, and move everything. So in those cases, placement tends to be very sticky. In this case, it's mostly all on the first NUMA node. In this case, almost all on the third NUMA node. The second interesting thing to see is that even though the placement is sticky, it still varies based on the load of different VMs. What this benchmark does, it varies load across different VMs over a period of time, and NUMA scheduler reacts to those load variations and try to make the best load balancing decisions in those cases. So that's why you see VM, even though migration is expensive, starts moving around. The third interesting point to see is that some dots tends to stay together. Right? If you look at these two guys, and these guys, and these guys, they tend to stick together. Why? It's probably because they talk to each other. When they talk to each other, there's data sharing. And NUMA scheduler knows about this, and we'll always try to place them closely together on a single NUMA node so that they can minimize the commission cost rather than go through and across the socket to a different NUMA domain. Cross-on-die. What is cross-on-die and how does it impact NUMA scheduler? So cross-on-die is basically breaking each socket into 2 different NUMA domains because the cores per socket is getting bigger. I think this applies to any socket with 10 or 12 more cores. So what this means is on ESX scheduler, we run a spec JBP 2015 benchmark on baseline system and cross-on-die system. What we see here is depending on the VM size, cross-on-die actually improved the throughput from anywhere from 4% to 8%. Why? First, spec JBP is very NUMA sensitive. And what cross-on-die gives us is a lower last lateral cache hit latency and lower local memory latency, and at the same time, a higher local memory bandwidth, so that if the workload is NUMA optimized, this is good. And 6.5 supports the cross-on-die from Haswell, Broadwell, and all the future generation processor that can be foreseen going forward. But our guideline around this is that we should always follow the BIOS of vendors, server vendors guideline of whether you should turn on cross-on-die or turn off cross-on-die. In those cases, NUMA scheduler will figure out and understand the distance between 2 NUMA nodes that are within a socket or across different sockets so that we can make the best decision. vNUMA. Let's quickly go through this. So vNUMA is basically one VM we break into 2 different virtual NUMA nodes, which applies to VMs which has more vCPUs than the cores per physical NUMA node. This exposing the virtual NUMA topology to the guest helps the guest decide what to run, which workload. Quick example, 10 vCPU VM, we have physical cores, 6 cores per socket. There is no way 10 vCPU can fit into a single NUMA node, single physical NUMA node. What ends up happening is that we will break the 10 vCPU VM into 2 virtual NUMA domains. Each is what we call a NUMA client, and we'll place each client onto a single physical node. Then everything should be okay. Confusions between vNUMA and vSocket. If we summarize all this in one sentence, ESX will try to make a decision for you going forward, starting from 6.5. You should only specify cores per socket if you really need to for licensing purposes. But for NUMA topology, 6.5 scheduler will figure out the optimal topology based on the host topology. What this means is that, say you have 8 vCPU VM. In old days, you configure 2 cores per socket for this VM. So we end up having 4 virtual sockets. In 6.0 and before, this gives a NUMA topology of 2 vCPU per NUMA node. But while at the same time, your host, in those cases, might have 4 cores per physical NUMA node, which makes this topology not optimal. What we should have is 4 vCPUs per NUMA node. And in 6.5, we know about this, and we actually make this decision of keeping the vCPUs, 4 vCPUs on single NUMA node, so that each NUMA node will have 2 virtual sockets. And this is good for performance. So the bottom line is that you don't need to worry about vNUMA as long as you don't give like weird numbers, like 11 vCPU VM, you have 9 cores per socket. If everything aligns properly with integer multiple, everything should be good. Quick example, 32 vCPU VM, 4 cores per socket, 8 socket. With the 6.5, we'll see is that we only have 8 socket, but 2 NUMA node here. 2 NUMA node, 2 NUMA node. This can be checked in the guest using NUMA control, LSTOPO, or core info from Windows. Lastly, host configuration and VM sizing. The only thing I want to talk about host configuration is power management policy, which is sort of counterintuitive if you think about this. This graph shows a high performance policy versus balanced policy. Different processor types, normalized performance. Balanced time, balanced throughput is higher. What's happening? So what's happening is that when you configure the power policy to balanced, the power scheduler or the power management policy takes in the input from scheduler and decide how deep a sleep each core should go into. But in the high performance case, we don't go really deep into the sleep taste, which means that there's less turbo, right? If you go to a deeper sleep state, you save more power so you can turbo more. And this improvement is based on how much turbo you can get. And balanced policy will give you a better turbo response because we take into the schedule. We know that, okay, you sleep for like 10 seconds for the last period of time, so you're probably not going to wake up really frequently, so that's put you into the deeper sleep state. So try balanced policy and probably give you a better performance going forward. VM sizing. Let's first talk about vCPU sizing. What's the cost of oversizing a VM? If your application developer tells you, hey, my application is awesome, I can use 8 vCPUs, 10 vCPUs, 20 vCPUs, no problem, please give me those vCPUs. Well, they're probably wrong because, well, they're probably right, but you don't know. You need to be careful. It's up to you, right? So what this means that why can't we just give them 20 vCPUs? Because each vCPU will be associated with a small overhead, which might be coming from periodic timers or coming from guest kernel contests. And this is less visible these days with the newer OS versions, but in the old Linux world, it's like 2.4 before, we have ticks per 10 millisecond, which is pretty bad. The more important case here of oversizing VM is that the guest scheduler may do some stupid stuff. For example, Redis workload, single-threaded Redis workload. What we see is that if we provision the Redis workload VM with 1 vCPUs because of single-threaded, and if we provision this into 8 vCPU VM. In 8 vCPU case, we're able to see a 40% regression of that single specific benchmark. What happened was that the guest doesn't know about hypervisor, right? The guest thinks that, okay, I have 8 vCPUs, I can just move this stuff around and try to be clever, try to load balancing. But at the end of the day, migration, as I mentioned before, is costly. If you configure the VM into 1 single vCPU, there's no chance the guest scheduler can kick in and migrate unnecessarily. In this case, we have a good performance. On the other hand, undersizing is also dangerous. Well, you cannot always tell people that I only give you 1 vCPU VM. You should be okay, right? This is because undersizing the VM triggers internal CPU contention in the guest where hypervisor may not able to help because we have no visibility into the guest scheduling. So what we should check? We should check 2 things. On the right, whether the usage of this VM shoots up to 100% every now and then. This is probably a sign of that the guest is trying really hard to schedule the workload inside the guest. And another thing we should check is in the guest, this is VM stats, we check the queue length. It's basically the length of the ready queue and how many threads it's trying to get to run at any given point of time. And this gives us a good indication of undersizing of a VM in terms of number of vCPUs. What about memory? Can we just give a lot of memory to the operating system, guest operating systems? The thing here is that a lot of applications, operating systems, treat in-use memory as cache because they think, okay, you're giving me 10 gigabyte, right? I'll just use the 10 gigabyte as cache, even though I'm not actually touching those memories. For example, superfetch. This trick in the guest actually drives up the active memory, which in turn may cause memory reclamation on the hypervisor level. Because even though your application actually only using 4 gigabyte, it may appear to hypervisor you actually have an active memory of 8 gigabyte. And we don't know about this. We will try to reclaim memory from other VMs to satisfy your cache, which is not very good. But again, everything has two sides, right? The cost of undersizing of VMs in terms of virtual memory is that you might have guest level paging. Guest level paging is that when you swap in the guest. What should we check? We should check the swap stats in the guest so that we make sure that there is no such thing as guest level swapping. And this is sort of guest level swapping stats. So we covered a lot of stuff. We talked about CPU scheduler, we talked about NUMA, we talked about memory, we talked about sizing and host configurations. Just to summarize, what's the key takeaway here? First, be aware of per VM ready time and per vCPU ready time, and always check the normalized one. Second, latency matters, and you should always pay attention to ready time. Third, we should size the VM properly according to number of cores instead of physical hyperthreads. Just because, when you have hyperthread contention, everybody runs slower. In 6.5 and beyond, a couple of new things. We have an overly insignificant, or like more and more insignificant overlap time. And some system time is actually moving to runtime to make it more intuitive. And though more hassle between vSocket and vNUMA, the guideline is that config cores per socket as you like, and leave the vNUMA decision to the host or ESX scheduler. And what I didn't mention before is that we always keep reducing the scheduling overhead of our resource management stack. So in 6.5, we actually have a significantly smaller scheduling overhead compared to 6.0 and 5.5. In terms of sizing or memory or capacity planning, we should always avoid active memory overcommitment and watch out for undersizing a VM because undersizing is dangerously invisible from hypervisor standpoint. In the end of the day, power policy matters. Remember the graph I showed you about balance versus high performance? Turbo mode actually matters here. So there's a couple of more talks happening here. I've graded out all the talks that already happened, but a couple of extreme performance series talks you might be interested in checking out. Performance best practice is going to happen like 30 minutes after this talk, which covers a more detailed statistic analysis on performance issues, where this talk is more focused on the scheduling policies side of the thing. Similar set of talks, a subset, is going to happen in Barcelona. Hands-on labs is a good opportunity to try stuff and play with VM configurations without breaking any actual product workload. I recommend you to try this. I actually tried it myself. It's actually very educational. So this year we have a new survey which is driven by performance team where we're trying to hear back from you about how you think about performance. What do you think about our product's performance? And feel free to scan this. I'll come back to this in a minute. As always, please fill out the survey. I'd love to hear your feedback and what do you want to hear? Do you want to hear about more futuristic things or more performance analysis things? And then hopefully we can tailor the talk better going forward. All right, with that, thank you very much.